Hello, good morning everybody. This is Mukherjee working as Associate Professor in St. Peter's Indian College. Today our topic of discussion is some fundamental properties of dielectrics. As we know, dielectrics is nothing but the study of insulators. Now, this video is mostly observed in a laptop or a desktop or a palm top or a mobile. Let us take the laptop or a mobile. Laptop or a mobile, however the best mobiles might be, however high-end the laptops might be, however a high configuration the laptop or a mobile, without a battery, they are of useless. Why they are of useless? Because without battery, there is no electrical power supply. When there is no electrical power supply, the mobile or the laptop will not work. So here, what is a dielectric? Dielectric is nothing but another study of insulators. And what is the relation between these insulators and dielectrics? Insulators are something which stores the electric energy, and that stored electric energy is used for our laptop or mobile, which is nothing but our battery. So batteries are nothing but they are made up of dielectric materials, and these dielectric materials are insulators, and insulators doesn't allow the electric charges, but they allow electric lines. Because they are allowing the electric lines, these electric lines are stored, producing a beautiful energy storage system. So dielectric is nothing but another study of insulators, or in short, study of a battery. So now the meaning of dielectrics. Dielectrics. Di means two equal and opposite. Electric means charges. So two equal and opposite charges, we call it as a dielectrics. So now dielectric materials. What are the dielectric materials? Basically, dielectric materials will have the electric dipole moments permanently. So these permanent electric dipole moments are going to produce the dielectrics. And what is an electric dipole moment? Electric dipole moment is nothing but a dipole with equal opposite and negative, positives and negatives separated by some distance. We have equal positives and equal negatives separated by some distance x. When we have equal positives, equal negatives separated by distance x, then is a beautiful Coulomb's force generated. But we know what is force? Rate of change of momentum. So when there is a momentum, if this momentum is going to change with respect to time, then force is generated. So force is nothing but the time dependent manifestation of the momentum. And that momentum, if it is produced between two equal or positives and negative charges, we call it as dipole moment. Two equal and opposites, pole, charges, momentum, the manifestation of the force. And by definition, it is defined as the product of charge into distance of separation. Let us assume that we have a plus q and we have a minus q separated by distance x. When we have plus q and minus q separated by distance x, the product of q into x produce a beautiful dipole moment, and the unit is coulomb meter or debye. So all the dielectrics are beautiful, fantastic insulators, but they are used to store electric energy. And batteries are beautiful insulators. And what are the best examples of all these things? Mica, glass, plastic, water, and other polar molecules. So now let us understand this from this diagram. Let us take a dipole. Here we have a positive plate and a negative plate. Between this positive and negative, we have a dielectric atom. Let us assume. No, dielectric atom in the sense insulator atom. What is an insulator atom? Any atom which satisfies the octet configuration, or a stable atom. Any stable atom is an insulator. Like, let us take this battery of mobile and battery of laptop. Battery of mobile and battery of laptop are made up of what? Lithium ion, not lithium. Lithium is a conductor, but lithium ion is an insulator. Why? Because when lithium loses one electron, it satisfies the octet configuration. When it satisfies the octet configuration, it becomes an insulator. So any ion which loses an electron or having an octet configuration is an insulator. So let us take such insulator. Such an insulating atom placed between the positive plate on left hand side, negative plate on the right hand side. So there is an electric field between the positive plate to the negative plate, where the electric lines are flowing from positive to negative. But in between, what is happening? The positive is trying to pull all the negatives of the atom, and the negative is trying to pull all the positives of the atom, but it's an insulator. And insulator will not accept an electron, will not leave an electron. It will not give an electron, it will not take an electron. So what what exactly it is happening is, let us take an example. A faculty is handling a classroom. Let us assume I am taking a classroom. When I am taking a classroom, all the student eyes and all the student ears are on the blackboard. But suddenly some disturbance is happening outside the classroom. When some disturbance is happening outside the classroom, what happens? The student eyes are still on the blackboard, the student ears are still on the blackboard, but their mind is not on the blackboard. Their mind is outside the classroom. Their mind is concentrated outside the classroom, but still they are in the classroom, physically present in the classroom. Their eyes are physically in the classroom, their ears are physically in the classroom. Similarly, all the electrons and all the protons are in the atom, but the only thing is that their direction, now all these electrons will look towards the positive plate and all the protons in the nucleus will look towards the negative plate. So what is happening? There is a change in the direction, and this change in the direction produces a distance of separation, and that distance of separation produces plus q minus q with some distance x. Dipole is produced. So now, to understand this, we need to have a dielectric constant, because this varies from element to element. Even though we have n number of insulators, one insulator is varying with respect to other insulator. So there is some material constant. And what is that material constant understood? With the help of dielectric constant. Now what is dielectric constant? Once again, a dielectric constant is the ratio of permittivity of the medium to the permittivity of free space. Now once again, what is permittivity? Permittivity is defined as to permit. Now what is being permitted? Who is permitting? The medium is permitting. And what is being permitted? The electric lines. A conductor permits the electrons. An insulator stops the electrons. But an insulator permits the electric lines. So an insulator is permitting the electric lines, and that is represented with epsilon. So epsilon gives the ability of the medium to permit the electric lines. So here epsilon r is defined as epsilon by epsilon naught. Permittivity of free space, permittivity of medium to the permittivity of free space. And that ratio will be a numerical value. And that numerical value doesn't have any units. It's only a concrete numerical value which identifies what is the capacity of a medium to allow the electric lines in comparison to the medium of free space. So now, using this, we need to understand the electric polarization. Now polarization, the name itself says polarization to produce poles. How many different types of poles we have? Two. What are they? Positive and negative are one kind of poles. North pole and south pole are another kind of poles. So what is polarization? The polarization is to generate the poles, to generate the positive and negative charges. When do you have this positive and negative charges? When a field is applied, the positive will be towards the negative plate and the negative charges will be looking towards the positive plate. And this change in the look, we call it as polarization. So the induced polarization or polarizability is defined as the mobility or dipole moment produced is proportional to the field intensity applied. So the induced dipole moment per unit electric field, we call it as polarizability, or mu equals to alpha E, and alpha I call it as polarizability constant, and this varies from element to element of an insulator. And for this we need to have, if we are going to have many such atoms, then we are going to add up all those polarizabilities and we produce a polarization vector. So the polarization vector P is given as the summation of the dipole moments per unit volume, which is given by P equals to sigma I equals to 1 to n qi xi by V, where Q is the number of charges separated by distance x. Now electric flux density. Electric flux density is defined as the charge per unit area. We also called as electric field displacement or electric flux density. And this is as defined as charge per unit area. Of course, it has the units of dielectronic polarization. So electric flux density is defined as charge per unit area. And once again, it is defined as D naught equals to epsilon naught into E, where D naught is the dielectric flux density or dielectric field displacement, which is proportional to the field applied, and epsilon naught is the permittivity of free space. If the same thing is happening in a medium, then the electric flux density or dielectric displacement in a medium D equals to epsilon naught into E. where epsilon is the permittivity of the medium, E is the applied electric field intensity. So we need to combine this equation 1 and equation 2, which is represented by D equals to epsilon naught E plus P, where D is the dielectric field density or electric flux density in a medium, which is equal to epsilon naught times the applied electric field intensity and polarization, which is represented in equation 3. So now combining these 2 and 3, we get epsilon E equals epsilon naught E plus P. Bringing all capital E terms to one side, we get epsilon minus epsilon naught into equals to P. And by definition, epsilon, which is derived from the relative permittivity, epsilon can be written as epsilon R into epsilon naught minus epsilon naught into equals to P. Take out epsilon naught common, we are going to get epsilon minus 1 into epsilon naught equals to P. So epsilon R is the relative permittivity, epsilon naught is the permittivity of free space, capital E is electric field intensity applied, going to produce the polarization P. So we need to define the susceptibility. What is susceptibility? Suspecting. If we are going to apply electric field intensity, what is the suspicion part? Or we are suspecting how much amount of electric lines are flowing through the medium, and that is what we call it as electric susceptibility, and is represented by chi subscript E. So therefore, the polarization vector is always proportional to the electric flux density and direction of electric field, which is represented by P bar equals to epsilon naught chi subscript E into capital E, or chi subscript E equals to P bar divided by epsilon naught E, and P bar is represented by epsilon naught into epsilon R minus 1 into E by epsilon naught E. So epsilon naught and E are getting cancelled out. Chi subscript E equals to epsilon R minus 1. The left hand side, chi subscript E, which is in the shape of X, we call it as chi. Chi subscript E, we call it as susceptibility. Epsilon R, the relative permittivity. So depending upon this electric susceptibility, the polarizations are classified into 4 categories: electronic polarization, ionic polarization, orientation polarization, space charge polarization. So let us see what is the electronic polarization. The electronic polarization, by name itself, it is happening among the electrons, in the sense it is happening in the atoms. It is happening in the atoms, we call it as electronic polarization. So when an EF, electric field, is applied to an atom, positive charge nucleus and the electron cloud will move in opposite direction, and this kind of displacement will produce electric dipole. So mu subscript E, electronic or electronic dipole momentum, mu E, is proportional to capital E, or mu E equals to alpha E into capital E, where mu E is the electronic dipole moment, alpha E is the electronic polarizability constant, and capital E is the applied electric field intensity. So now, and it increases with increase in the volume. Anyway, we are going to derive that in the next article. But this kind of polarization, electronic polarization, because it is happening only in the atom, it is mostly of monoatomic gases. The typical value of electronic polarization is of the order of 10 power minus 40 farad meter square. Now let us see, there are examples, inert gas examples like helium, neon, argon, krypton, xenon. If you take helium, what is the value of helium? It is 0.18 into 10 power minus 40 farad meter square. If you take neon, the neon value is 0.35 into 10 power minus 40 farad meter square. If you take argon, it is of the ratio of 1.46 into 10 power minus 40 farad meter square. If you take krypton, it is of the ratio of 2.18 into 10 power minus 40 farad meter square. Xenon, it is in the ratio of 10 power minus 40 farad per meter square. Now what is happening? Helium to xenon, the atomic number is getting increased. Atomic number is getting increased, the number of electrons and protons will also get increased. And therefore what is happening? The radius is getting increased. Implies the volume is getting increased. Implies when the volume increases, even the value of electronic polarizability is also getting increased. Bigger is the volume, bigger is the radius, bigger is the volume, more is the capacity of the electronic polarization. Implies more is the capacity to store the electric charge. And this mostly occurs at the optical frequencies of 10 power 15 hertz, a very high frequency range. So this is very fast. This is very fast, and it is independent of temperature. So the expression for electronic polarization. Let us derive the expression for electronic polarization. Let us consider an atom. When it is placed in an electric field intensity capital E, let us assume that nucleus has a charge plus Ze and electron cloud has a charge minus Ze, and both of them are separated. Let us call that as a Lorentz force. So when field is applied, what is happening? The nucleus moves in the direction of the field and electron cloud moves in the opposite direction. In short, the nucleus moves towards the negative plate and electron cloud moves towards the positive plate, still in the atom. So when electron cloud and nucleus get shifted from their normal positions, what is happening? A beautiful separation, distance is produced, and that is going to produce Coulombic force, and that is balanced by the Lorentz force. So let us see all these things mathematically here. Let us take an atom whose radius is r. Exactly at the center we have a dot. In figure 1 we have a central black dot, and that central black dot is the point where plus z is located, and say minus z is also located there. So the black dot in figure 1 where there is no field, the plus z and minus z are coinciding, are meeting with each other. So there is no distance of separation. But when we apply field, what is happening? There are two dots in figure 2. In the presence of field, what is happening? There are two dots, and one dot, central dot, is represented by plus z, and the right side dot is represented by minus z, and now there is a distance of separation x. So taking that, let us draw a small circle in the bigger circle. So now we have two circles, bigger circle with radius r, smaller circle with radius x. So we are going to take these things. So figure 2 represents the displacement of nucleus and electron cloud. We assume that the negative charge in the cloud is uniformly displaced or disturbed over a sphere of radius r, and the spherical shape does not change for convenience. It is only for understanding. So now let us define the charge density. Now what is charge density? Charge density is defined as the charge per unit volume. Now what is charge? Electronic charge, because we can only discuss with respect to the electronic charge. Minus z is the electronic charge. And what is the volume? 4 by 3 pi r cube. That is the normal original volume. So minus z by 4 by 3 pi r cube, where r is the radius of the atom. Now we apply the electric field. When we apply electric field, what is happening? When we apply electric field, a small circle with radius x is produced. So let us find out how much amount of charges are there in this circle of radius x. How to find out? It is simple. To find the charges in the sphere of radius x, we need to multiply the charge density into new volume. So charge density sigma into new volume 4 by 3 pi x cube. But already we have defined sigma as minus z by 4 by 3 pi r cube. Substitute that value in this equation. What is that we get? Minus z by 4 by 3 pi r cube into 4 by 3 pi x cube. So 4 by 3 pi in the numerator, 4 by 3 pi in the denominator, they get cancelled out. We are left out with minus z x cube by r cube, equation 1, which implies the charges available in this sphere of radius x. Now let us take the Coulomb's force. What does Coulomb's force say? Coulomb's force is given by QE q by 4 pi epsilon naught x square. QE, charge of electron. QP, charge of proton, separated by distance x. Or 1 by 4 pi epsilon naught x square into QE, already we have derived from equation 1, minus z by r cube x cube. Substitute that value in this. We get minus z x cube by r cube into z. So when we combine the whole equation, we get minus z square e square x by 4 pi epsilon naught r cube, which is equation 2. So now the force experienced because of this electric field making this positive charges and negative charges getting displaced, we call that as the Lorentz force, which is given by FL equals to capital into small q, which is given by Z into E. Let us assume this to be equation 3. So now already we discussed that the Lorentz force is balancing the Coulomb's force. So FL equals to FC. Now equate equation 2 and equation 3. We get minus Z square E square x by 4 pi epsilon naught r cube equals to Z into E. Or you can cancel out one Z on the right hand side and one Z on the left hand side. We get capital E equals to minus ZEX by 4 pi epsilon naught r cube, or minus ZEX by 4 pi epsilon naught r cube equals to capital E. But how do we define the electric field intensity? Electric field intensity defined as dipole moment per electronic polarizability alpha E. So substitute that value, we get minus ZEX by 4 pi epsilon naught r cube equals to minus ZEX by alpha E. So just cancel out minus ZEX and minus ZEX in the numerator, equate the denominator, we get alpha E equals to 4 pi epsilon naught r cube. So alpha E in this 4 is constant, pi is constant, epsilon naught is constant, the only variable is r. And what is r? The radius of an atom. And what is r cube? The volume of an atom. So alpha is proportional to the volume of the atom. Bigger is the volume, bigger is the electronic polarizability. Bigger is the electronic polarizability, huge is the capacity of that atom to store electric energy. Implies it can store a huge amount of electric energy. Hence, the electronic polarizability is directly proportional to cube of the radius of the atom. Now let us go to the next polarization, ionic polarization. And this ionic polarization mostly happens between the atoms or ions, specifically ions. And that too ions or ionic molecules. And this is due to the relative displacement of the atomic components. Let us assume that we have two ions, X1 and X2, like sodium chloride. Na, let us assume X1 to be sodium, X2 to be chlorine. So what happens in sodium chloride? Na loses one electron, becomes sodium ion. Chlorine gains one electron, becomes Cl minus. So now Na plus and Cl minus, now this is a beautiful insulator. And this sodium also corresponds to the family of lithium. That is what the lithium ion batteries. We don't have lithium batteries. We justly have lithium ion batteries, because lithium ion or sodium ion are a beautiful insulators. So sodium is losing an electron, chlorine is gaining an electron, transfer of electron, producing a bond there. It's a beautiful, fantastic, dielectric element. So the resultant dipole momentum is, when we apply field, what is happening? The dipole moment is given by Q into X1 plus X2. Now what is X1? The distance moved by the sodium. What is X2? The distance moved by chlorine. Or what is X1? The distance moved by the positive ion. What is X2? The distance moved by the negative ion. Now this is what the diagrammatic representation is. When we apply electric field, what is happening? The cation is moving towards the positive plate and anion is moving towards the negative plate. The cation towards the positive plate, anion towards the negative plate. But cation will not go and stick to the positive plate, anion will not go and stick to the negative plate. The positive charges will not go and stick on the cation, the negative ions will not come and stick on the anion, because still the cation and anion are bonded to each other, but there is only increase in the distance, like rubber band. You take rubber band, put between two fingers and try to stretch the fingers. So what is happening? The rubber band is getting expanded. Something similar to this cation and an anion, they are getting expanded, and between them the distance is measured with respect to the center as x1 for cation, x2 as the anion. So now let us assume that a restoring force constant depends on the mass of the ion, because the only thing what we can measure is the mass of an ion and the frequency with which the field is applied. In general, by definition, when we have a charge electron placed in electric field intensity, the force is given by small e into capital E. Similarly, the mechanical force is given by m omega naught square into x. So F equals to small e into capital E equals to m omega naught square x. Now we equate them. What is that? We get the value of x. X equals to small e into capital E by m omega naught square x. As the cation is moving with the distance x1, anion is moving with the distance x2. Let us assume the m is the mass of the cation, small m is the mass of the cation, capital M is the mass of the anion. So x1 plus x2 can be written as small e into capital E by omega naught square into 1 by small m, the mass of cation, plus 1 by capital M, the mass of anion. So the mu ionic dipole moment is given by charge into distance of separation, E into, now here you have two distances with respect to the center, we call it as E of x1 plus x2. Already we have derived the x1 plus x2 value from the above equation. X1 plus x2 equals to small into capital M by omega naught square into 1 by small m plus 1 by capital M. Substitute that value here. We get E square capital M by omega naught square into 1 by small m plus 1 by capital M. Or alpha ionic. The ionic polarizability constant is given by the ionic dipole moment divided by applied electric field intensity, mu ionic by capital E, which is given by E square by omega naught square into 1 by small m, the mass of cation, plus 1 by capital M, the mass of anion. And this is the ionic polarization. And this occurs at a frequency of 10 per 13 hertz of IR, in the sense infrared frequency. And it is a slower process compared to the electronic polarization. But electronic polarization, ionic polarization, both of them are independent of temperature. So the fastest polarization is electronic polarization, followed by the ionic polarization, which is a bit slower compared to the ionic polarization. And the third one is the orientational polarization. It's also called as dipolar or molecular polarization. Like you take molecules like hydrogen, H2, N2, O2, Cl2, CH4, CCl4, etc. They don't have any dipoles, because the center of positive and center of negative always coincides. But on the other hand, molecules like CH3Cl, H2O, HCl, ethyl acetate, they carry a very little dipole moment even in the absence of electric field. So the net dipole moment is actually very small, since the already available molecular dipoles are oriented randomly. But when you apply electric field, they align themselves to the field we just applied. And that is with the name itself, orientational, orienting. So the little dipoles which are present, they try to orient themselves to the applied field. We call this as orientation dipole moment. And it occurs at a frequency of 10 power 6 to 10 power 10 hertz. Of course, it's a very slow compared to the ionic polarization, but it depends on temperature. This orientation polarization depends on temperature. Anyway, we are not going to go to the mathematical details of this. We are going to go to the net result of the orientation polarization. The orientation polarization is given by n into mu orientation polarization, or P naught equals to n mu square E by 3 kt, or n alpha naught E, or alpha naught equals to mu square by 3 kt, where mu or E is the orientation dipole moment, K is the Boltzmann constant, capital T is the temperature. So the total polarizability available in the system is given as electronic polarization plus ionic polarization plus orientation polarization, alpha elect plus alpha ionic plus alpha ori, which is given by 4 pi epsilon naught r cube plus E square by omega naught square into 1 by small m plus 1 by capital M plus mu square ori by 3 kt. And we call this equation as Langevin-Debye equation for the total polarizability in a dielectric, because mostly dielectrics, they will be in a complex quantum. So among this complex, it may be a combination of electronic and ionic and orientation, electronic orientation, or all three, or all individual. Now, we have derived what are the different types of polarizability we have, but we need to know how much they are storing, how much amount of energy is stored, how much total energy is stored. And that energy stored, or that energy stored, we call it as internal field or local field, is also called as a Lorentz field. So what is the local field? The local field is the energy or a field in a dielectric which is generated because of the time varying electric field intensity acting on a particular molecule of a dielectric. So when a dielectric is taken, it is placed in a time varying electric field. When it is placed in a time varying electric field, some amount of energy is stored, and that energy is stored, we call it as internal field or local field. So let us derive this. Let us consider a dielectric placed between plates of parallel plate capacitor, and let there be an imaginary spherical cavity with an atom A. Now let us see. And there we are going to have 4 different types of components, E1, E2, E3, E4. First let us see the diagram and understand what is this E1, E2, E3, E4. So this is what the diagram is. What is happening? We have a charge, we have a battery, we have a potential charge from which the positive is connected to the red colored plate where you have only positive charges. The negative is connected to the red plate where we have negative charges. So now we have positive charges in red, negative charges in red. In between that we have a dielectric material. So what is this positive doing? It is trying to pull all the negatives, and what the negative in red is doing? It is trying to pull all the positives. So what is happening? All the negatives of the dielectric material are getting deposited on the green color line towards the positive of red, and all the positive are deposited along the green color line towards the negatives in the red. So what is happening? A displacement is happening. Now what is this positives along the green and negatives along the green are doing? Let us assume a spherical cavity. So this negative along the green are trying to pull the positives along the blue. And what are the positives along the green are trying to do? They are trying to pull all the negatives along the blue. So now positives along the blue are aligned because of negatives along the green. And the negatives along the blue are generated because of the positives along the green. And negatives along the green are generated because the positives in the red. And the positives along the green are generated because the negatives in the red. So now we have 4 different fields, E1, E2, E3, E4. Now what is E1? The red in the positive is generating electric line from positive in the red to the negative in the red. We call it as E1. And what is E2? The positive at the green is generating line to the negative in the green. So positive in the green to negative in the green. We call it as E2. And what is E3? Let us assume E3 to be 0, assuming that in the sphere there are no atoms. Now what is E4? The positives along the blue are generating the electric lines towards the negatives along the blue. And let us call it as E4. So we need to find out E1, positive in the red to negative in the red. E2, positive along the green to the negative along the green. E4, positive along the blue to the negative along the blue. And all these 3 fields are acting at point A. And what is the other thing? Positive in the red to the negative in the red. if it is positive, the positive in the green to the negative in the green is opposite to positive in the red to the negative in the red. So both of these electrics are opposite to each other. So let us put in a mathematical format. Now what is E1? E1 is the field intensity at A due to charge density on the plates. That is positive in the red, negative in the red. By definition, E1 is given by d by epsilon naught, where d equals epsilon naught E plus P. So E1 equals to epsilon naught E plus P by epsilon naught. Or E1 equals to E plus P by epsilon naught. So what is E1? The electric field intensity generated between the positives in the red to the negatives in the red. So now let us go to the second level. Field E2. Now what is E2? E2 is the polarizations per the field intensity, the polarizations per the permittivity of free space. Et equals to minus P by epsilon. What is E2? The positives at the green to the negatives in the green. And this is opposite to positives in the red to negatives in the red. That's the reason E2 is taken as minus P by epsilon naught. Now what is E3? Already we assume E3 to be 0. Now what is E4? Now let us take the macroscopic view of the surface there. The positives are all aligned above the plane and negatives are all aligned below the plane, which is a spherical, where R is the radius. In that we are going to divide PQ into QR, where QR is the sector, and this QR sector has a angular displacement, angular variation of d theta at center A, and this QR is aligned at an angle theta at A. So QR sector is inclined at angle theta at A, having an angular separation of d theta at A. So this is the macroscopic view, and dA we are going to take one circular surface of that spherical whose area is dA. So now let us take this and try to evaluate the total field. Now what is area? We know that area is nothing but 2 pi into PQ into QR. Let us go back to the diagram. What is dA? dA is nothing but length into breadth. Because it is a spherical surface, 2 pi into PQ. What is PQ? The radius of one circle. And what is QR? The sector of that circle. So what is the area given by 2 pi into PQ into QR? But what is PQ? Once again get back to the diagram. What is PQ? APQ is a right angle triangle from which we get PQ equals to R sine theta. And what is QR? Of course QR is a sector, so sector length is always given by radius into angular separation, so QR is given by R d theta. R sine theta, R d theta. We are going to substitute in this. We are going to get dA equals to 2 pi R sine theta into R d theta, or 2 pi R square sine theta d theta. This is the area. Now how do you define the total charge? The total charge is given by the polarization into the area. Here the polarization is represented by P. So we are going to take P cos theta into dA. Now why P cos theta? Why not P sin theta? Let us go back to the diagram. When we go back to the diagram, what is happening? All the charges, all the charges are distributed above the plane or below the plane. So the net implies that the positives are along the positive of y-axis and the negatives are along the negative of y-axis, and therefore the positive along y-axis and negative of y-axis are going to cancelling the P component along the vertical, and therefore we are only left out with P component along horizontal, which is P cos theta, and therefore we are taking P cos theta. So let us get back to this. What is that? We have dQ equals to P cos theta into dA, and already we have derived dA. What is the dA here? The dA is defined as 2 pi r square sin theta d theta. So what is that? We are going to get 2 pi r square P cos theta sin theta d theta, which is the total charge available. So now the field is given by dE4 equals to 1 by 4 pi epsilon naught r square into dQ. But here, what is that we are taking? We are not taking dQ, we are taking dEQ cos theta. Once again the same concept. Get back to the diagram. What is the diagram we have? In the diagram, what is that we have? All the positives are along the positive of y-axis, negatives are along the negative of y-axis. So which implies that the vertical component is reduced to 0 and we are only left out with the horizontal component, and therefore the charge is evaluated with respect to the horizontal component as dQ cos theta. So therefore this is represented as dE4 equals to 1 by 4 pi epsilon naught dQ cos theta by r square. Already we have derived the dQ value as given 2 pi r square P cos theta sin theta d theta. Substitute this value here. What is that? We get dE4 equals to 1 by 4 pi epsilon naught r square into 2 pi r square P cos theta sin theta d theta cos theta. Now 2 pi r square, they get cancelled out. What is that we are left out with? P by 2 epsilon naught cos square theta sin theta d theta, and now we need to integrate this because we have a d theta, we need to integrate. Now what are the limits for this theta? Let us go back to the diagram. When we go back to the diagram, what is that we have? All the positives and all the negatives are distributed along the positive of negative of y-axis. So let us take this. On the right hand side of the circle, what is happening? The positive and negative separation is happening. On the left hand side, the positive and negative separation is happening. So positive and negative separation is happening at 0 degrees, and it is getting ended up at 180 degrees on the left hand side. So the angles for the integration are 0 to pi, 0 to 180. So let us go back and derive that equation. So here E4 is given by integral 0 to pi dE4, or which is given by 0 to pi p by 2 epsilon naught cos square theta sin theta d theta 0 to pi, or p by 2 epsilon naught 0 to pi cos square theta sin theta d theta. Let us assume x equals to cos theta, dx becomes minus sin theta d theta, and substitute the value of d theta dx there. P by 2 epsilon naught integral 1 to minus 1 x square dx minus p by 2 epsilon naught into x cube by 3 within limits of 1 minus 1. In place of x, substitute minus 1. Once again, in place of x, substitute 1. We get minus p by 2 epsilon naught minus 1 by 3. Minus 1 becomes minus 2. 2 and 2 get cancelled. Minus into minus plus. We get p by 2 epsilon naught is E4. So the total field is given by internal field, or Lorentz field is given by EI equals to E1 plus E2 plus E3 plus E4. Already we have defined E1 as E plus P by 3 epsilon naught. E2 as minus P by epsilon naught. E3 anyway 0. E4 is given by P by 3 epsilon naught. So it is EI equals to E plus P by 3 epsilon naught. And this EI equals to E plus P by 3 epsilon naught is the local field or the Lorentz field. And this is the amount of field that is stored actually in the dielectrics. So with this, today we are going to end the topic of discussion of dielectrics. Tomorrow we will see some other properties of dielectrics and magnetic properties.